Hey there, stat students. In today's video, we're going to take a look at a couple important ideas. We're going to learn about conditional probability and independent events. So first, we'll start out with a question about probability. So here we've got 8 Mario Kart characters, and simple question about probability to start with is if one of these people were selected at random, well, what is the probability that that person would have a mustache? Well, looking at this, you can consider these 8 to be the sample space. You know, we could pick Mario, Luigi, Peach, Toad, and on and on. That's our sample space. Those are the outcomes that we could pick. And if we're picking at random, we can assume that there would be a 1 in 8 chance of picking any one of these characters. So the probability that we pick someone that has a mustache would require that we would randomly pick Mario or Luigi or Wario. So those 3 out of the 8 would be the 3 that would meet the conditions for that event. And so the probability that we would randomly pick someone with a mustache would be 3 over 8, or 3/8 or 0.375. I want to ask you a similar question with one extra little twist to it. If one person below is selected at random, what is the probability that they have a mustache given that they are wearing a hat? So in this question, now you have a little additional information about the person that's being picked, is that they're wearing a hat. And I want to note here that Toad is not wearing a hat. That is just part of his head. So Toad not wearing a hat. So if we are given that we're selecting someone with a hat, well, that kind of narrows the frame down. So we're not looking at everybody in the sample space. We're only looking at the people with hats. So Mario, Luigi, Peach, and Wario are the 4 individuals in the population that are wearing hats. So Yoshi and DK, we're ignoring them for right now, and Toad and Bowser, we're ignoring them because they do not wear hats. So given that the person we're selecting is wearing a hat, now we're only choosing from these 4 individuals. And still we could choose Mario, Luigi, or Wario. They have mustaches. But now the probability is not 3/8 anymore. Now the probability is 3 over 4. And what really changed here is the fact that we were given additional information. It was given that this person was wearing a hat. What's the chance they have a mustache? So we're only looking at the 4 people with the hats. So really what this comes down to is when we're looking at a given piece of information, we are no longer taking from the entire set of individuals or looking at all of the outcomes in a sample space. We are only looking at a subset of individuals, in this case, who are wearing hats. In other words, you were focused only on the people who met a specific condition. The condition was that they were wearing a hat. And for this reason, since the people we were selecting had to meet a condition, we have a name for that probability, and it is called a conditional probability. Toad and Bowser and DK and Yoshi, they did not meet that condition of wearing a hat, and so we ignored them when we found that probability and only looked at the 4 that did meet that condition. Mario, Luigi, Peach, and Wario, they were wearing a hat. So conditional probability is all about narrowing the focus down, not out of all outcomes, but only out of the outcomes that meet a specific condition or criteria. There's a really important formula that you'll need to know and be able to use. For events A and B, the probability of A given B follows this formula. In this notation here, this vertical line really just means the word given. So here, this is communicating what is the probability of event A occurring given that event B has occurred. So knowing that event B occurs, what's the chance that A occurs as well? And the formula for that A given B is to divide the probability of A and B divided by the probability of B. So out of the times that B happens, how often does A also happen? That is a very important formula to know. You will be putting that to use in AP Stats throughout the probability unit quite a bit. To break this down just a little bit, what this fraction means here is that out of the times that B occurs, so the denominator is B, we're narrowing the focus down only to the times when event B, whatever that is, whenever that occurs. So out of the times that B occurs, how often does A also occur? And that's why we take A and B occurring together out of all of the outcomes in which B occurs. And that is the conditional probability of A happening given that B happened. So we'll take a look at a few examples of using this formula, finding some conditional probabilities. So this Venn diagram shows the probabilities of customers selecting a couple different pizza toppings. And I know these are not all the pizza toppings they can select, there's just a couple of them. So a lot of people like to put pepperoni on their pizza, on one of them. And some people like to put mushrooms on their pizza, on one of them too. And some people out here don't like to put either of those toppings on their pizza. And so there's the section outside where these people are not getting pepperoni at all. So we have this section here, this 0.6, they get pepperoni, but they don't get mushrooms. This 0.04, they get mushrooms on their pizza, but not pepperoni. This 0.01 is people getting both pepperoni and mushrooms. And this 0.35 refers to people that don't have either of those toppings on their pizza. Maybe they have other toppings, maybe not, but pepperoni and mushrooms are not on their pizza. So I wanted to find two events here. We'll use capital letter P to represent that pepperoni was selected for the pizza, and M, that mushrooms were selected for the pizza. So before we get to conditional probabilities, just understanding the scenario a little bit, what is the probability that pepperoni is selected on their pizza? Well, these two sections that make up this circle need to be combined because everyone in this circle would get pepperoni on their pizza. So 0.6 plus 0.01 would be 0.61, would be the probability that they get pepperoni on their pizza. What's the probability to get mushrooms? Well, that would be 0.01 plus 0.04, which would be 0.05. 5% of people get mushroom on their pizza, and 61% of people get pepperoni on their pizza. And I'm realizing now that I have a, no, I don't, I'm good. Never mind. All right, so let's take a look at some examples of some conditional probabilities. So in this first one, I want to know what is the probability of getting pepperoni given that they've selected mushrooms. In other words, what that means is out of the times where people select mushrooms, how often do they also select pepperoni on their pizza? So the probability of getting pepperoni given they've gotten mushrooms is the probability of pepperoni and mushrooms over the probability of mushrooms. So substituting in these values, the chance of pepperoni and mushrooms is 0.01. The probability of getting mushrooms on the pizza is 0.05. So 0.01 divided by 0.05 would simplify to 0.2. So knowing that a person gets mushrooms on their pizza, there's a 20% chance that they will also get pepperoni. Or out of these customers who choose mushrooms, 1/5 of them also choose pepperoni on their pizza. What if we flip it around? In this case, I want to know what is the probability of a person getting mushrooms on their pizza given that they've gotten pepperoni on their pizza. This would be a great time to pause the video and try to find this probability on your own. And when you're ready to press play again and see if you got it right. Well, let's see what we've got. So using this formula, the probability of mushrooms given pepperoni is the probability of mushrooms and pepperoni divided by the probability of pepperoni. Well, the probability of mushrooms and pepperoni together is 0.01 divided by the probability of pepperoni is 0.61. And when you simplify that down, you get approximately 0.016. So about 1.6% of people who get pepperoni on their pizza also get mushrooms on their pizza. So there are not a lot of people, if you know they get pepperoni, mushrooms are not popular with that crowd. Very rare that people who get pepperoni are going to throw mushrooms on there too, according to these probabilities. All right, well, let's take a look at another example. This table here shows the proportion of students who are either in person or remote, and who are in the AM session or the PM session in a geometry class. So this table shows here that if you look at the total of the AM, that half of the class is in the AM session, and then the other half is in the PM session. And you can see that there's like an 80-20 split between in-person and remote, where 80% of the class is in-person and 20% are remote. And the overall total is 1, and that accounts for all students, all 100%. Breaking these down, there are 35% of the class are in person in the morning, and 15% are remote in the morning. 45% are in person in the PM, and 5% are remote in the PM, just to kind of understand what this table is describing. So let's say one student is going to be selected at random from this class. Given that the student is remote, what is the probability that they are an AM student? This will be a good time to pause the video and see if you can find that probability. Given that the student is remote, what is the probability that they are an AM student? All right, let's see what we've got. So I always like to start out with a formula and use the probability notation because that helps me make sense of how to set up the fraction, what divided by what. So we're looking at this probability. What is the probability that a student is in the AM given that they are remote? To find that, we need to find the probability of them being AM and remote and divide that by the probability of remote. So AM and remote is this 0.15. That's the joint probability of students who are both remote and in the AM session. And that's divided by this 0.2. We are ignoring all of the in-person students here because it's given that the student is remote. So we're only looking at the 20% who is remote, and 15% divided by 20%, or 0.15 divided by 0.2, is 0.75. Looking at these remote students only, 75% of them are in the AM session. And that would leave 25%, I suppose, in the PM session. Let's take a look at another one. So again, we're selecting one student at random from this class. Given that the student is a PM student, what is the probability that they are in person? So we are only focused on the PM students here. We are not interested in the AM students right now. It's given that they're a PM student. Well, setting up the formula and using the probability notation, we're looking to find the probability of them being in person given that they're a PM student. Using that formula, we'll find the probability of them being in person and PM divided by the probability that they are PM. So looking at the table, we have 0.45 is the probability that they are both in person and PM. So that's brought down here to the numerator. And that is out of the PM students, which are 0.5. So out of the half of students who are in the PM, how many of them are in person? And so 0.45 divided by 0.5 will be 0.9. And that means that roughly 90% of students from the afternoon are in person. This is 90% of that PM session right here in the in-person class. All right, so from those examples, you should have an idea of how to use and find conditional probability. Really make use of that formula as much as you can. And I really strongly recommend that you write things out using probability notation first, and then dive into using the numbers and actually doing the math. One last thing that we'll talk about here is the idea of independent events. Events A and B are defined as independent if this is true about those two events. If the probability of A equals the probability of A given B, then events A and B are defined as independent. And essentially what this means is that event A is independent from event B if A has the same chance to occur, regardless of whether B also occurs. So if you know that B occurs, and then A happens at the same chance it was going to anyway, that means that A does not depend on B. Knowing that B occurred didn't change the chance of A happening. And if that's the case, then A and B are considered to be independent. However, if the probability of A is not equal to probability of A given B, then they're not independent, because knowing that B occurs changes the chance that A occurs. And so A depends on B. The additional knowledge we get from B occurring changes whether or not A will occur, how often A will occur. Thinking back to that original example of choosing a random Mario Kart character, when you chose out of everybody, there was a 3 out of 8 chance of picking someone with a mustache. Knowing that a person was wearing a hat, there was a 3 out of 4 chance of picking someone with a mustache. So when it comes to Mario Kart, wearing a hat and having a mustache are not independent. They're dependent on each other, because wearing a hat made it much more likely for that character to have a mustache. So going back to this example about the AM, PM students, in-person remote students, I want to know if the events being an AM student and a remote student, are those independent? So knowing one piece of information, does that change the probability of the other one? In checking whether they're independent, this is what we need to check. Is the probability of them being an AM student equal to the probability of them being AM? Let me say that again. Is the probability of them being an AM student equal to the probability of them being an AM student, given that they are a remote student? So if we can check and this gives us the same thing on both sides exactly, then they're independent. If we check these two things and they're different, then they're not independent. Simple as that. Well, I'm going to rewrite this conditional probability using the formula. AM given remote is AM and remote divided by remote. So let's substitute in the values that we know. The probability of being an AM student is 0.5. And the probability of being AM and remote is 0.15. The probability of being remote is 0.2. So if this were to simplify to 0.5 to match the other side, then they'd be independent events, but the right side will simplify to be 0.9. So 0.5 is not equal to 0.9. That means these two events are not independent. Being an AM student and being remote, they are dependent on each other. Knowing that a student is remote makes them far more likely to be AM than they would be without that piece of information. And so for that reason, they are not independent. If you are trying to show independence, this right here, this is the math that you need to show. You need to show that you are checking whether or not this statement is true about the two events. If you get the same amount on both sides, great, they're independent. If you get different amounts, great, they're not independent. So from this video, you should be able to calculate and use conditional probabilities, and you should be able to check whether or not two events are independent using this definition in this mathematical check.